Welcome. In this video, we're going to go over a different optimization problem. In this one, we're interested in maximizing the area of a space given a certain amount of material to bound the space. And we will be using 6 steps to solve this problem. These are the 6 steps we will follow for solving optimization problems. Step 1, make a sketch. Use that sketch to identify the objective and constraint functions. Step 2, combine the constraint into the objective function. Step 3, find critical values of the objective function. Step 4, confirm critical value is desired max or minimum. I should add here to step 2 that you are required to reject any unrealistic critical values. For example, you cannot have negative fencing for a perimeter. Step 5 then is to use the remaining critical value in the constraint to solve for any unknowns. And then step 6, answer follow-up questions. So you are interested in creating a fenced-off catio so your indoor cat may relish the outdoors. You have an ample backyard and plan on attaching the catio to your house so that the back door opens into the space. Hence, fencing is only needed along 3 sides. There are 50 feet of fencing available for the sides of the catio. What dimensions will maximize the area available for your feline's enjoyment? And so in this problem, we're ignoring the fact that a catio needs a roof. So we're just sticking to the sides of the catio space. So let's begin with a picture. And now this here isn't necessary. This is just the back door. So here is the home, meaning this part here, these dotted lines, are the only fencing that will be used. And let's call this X here and this Y. Now let's use this picture to find our objective and constraint functions. And to keep track of what we're doing, let's go ahead and write the steps down. So our first step, which we're working on right now, is to make a sketch and use that sketch to identify the objective function and the constraint. So our objective here is to maximize the area. So our objective function is area equals x times y, since that would be the area of a rectangle. Our constraint function, however, is given by the fact that we're constrained to just 50 feet of fencing. So that means the perimeter, which is given by 2x plus y, is equal to 50. Next, let's move on to step 2. And in step 2, we're going to combine this constraint into the objective function. And we can do this by solving for y, that is y equals 50 minus 2x. So our objective as a function of x is equal to x times 50 minus 2x, or just 50x minus 2x squared. And so there is step 2. Next, for step 3, let's go ahead and find the critical values of the new objective function. And we find the critical values by first finding the derivative of our new objective function, and that is equal to 50 minus 4x. And when this function equals 0, we know we have a critical value. This function only equals 0 when 4x is equal to 50, or equivalently, x is equal to 12.5. Next, let's move on to step 4. And in step 4, we're going to confirm the critical value we found is the desired minimum or maximum value. In our case here, we're looking for a max, since we're looking to maximize the area. So let's just start with a number line. And on this number line, let's go ahead and mark where we found 12.5. So that is the critical value we found on a number line. I think everyone would agree that x equals 10 is less than 12.5. And I also think everyone watching this video will agree that x equals 15 is more than 12.5. And we want to find a prime of 10 and a prime of 15. Namely, we want to see if the derivative, that is the slope of the tangent line of our objective function here at x equals 10 is positive or negative. And we want to do the same thing with the slope of the tangent line at 15 of this objective function. Is it positive or is it negative? Okay, so how can we do that? Well, let's go ahead and evaluate. That is a prime of 10 is equal to 50 minus 40, which is just 10. So this is positive. And a prime of 15 is equal to 50 minus 60, which is negative 10. So the slope of the tangent line to the left of our critical value is positive, so going uphill. And the slope of the tangent line to the right of our critical value is negative, going downhill. And when a line travels up and then down, the point here, the critical value, is indeed a max, just as we desired. Now that we've confirmed that the critical value is indeed a max, we can move on to step 5. That is, we can use the critical value in our constraint function to solve for any unknowns. So our constraint is y equals 50 minus 2x, but of course we figured out that x is equal to 12.5, so let's substitute that in here. So this is equal to 50 minus 2 times 12.5, which is y equals 25. Finally, we can move on to the very last step, step 6, and that is answer any follow-up questions. So here is step 6, and the follow-up question is, what dimensions will maximize the area available for our feline's enjoyment? So the dimensions would be a width of 12.5 feet and a length of 25 feet will maximize the area of the catio.